Thanks for joining me today. In the world of switched capacitor signal processing, ring amps are starting to grab some attention. Year after year at ISSCC and other top conferences, they're helping to break ADC performance records and advance the state of the art. There's a lot of hype and interest surrounding the topic, but also quite a bit of skepticism, confusion, and misconceptions. In this talk, I hope to bring some clarity to all of this. I'm going to start by motivating the need for ring amps, and then dive into fundamentals and basic principles of operation. We'll then look at how to choose the best ring amp topology for a given application. After that, I'll walk you through a decision tree for how to optimize your ring amp towards any particular performance priority, such as high speed or high accuracy. Finally, we'll tie it all together in a practical design example and discuss how to design and validate in cadence. To motivate the general need for new amplification solutions in advanced technologies, I'd like to begin with a look at some of the clear scaling trends that we can observe in ADCs. As designers have moved into nanoscale technology nodes, some ADC architectures clearly downscaled better than others. Perhaps more than any other, the SAR ADC has been particularly successful, delivering the state-of-the-art across an incredibly wide range of applications, from ultra-low speed biomedical and sensors up to ultra-high speed wireline. On the other hand, many ADC architectures that once dominated large regions of the ADC application space have been pushed to the fringes. For example, pipelined ADCs were once considered the solution for high-speed ADCs above a certain resolution. Now, interleaved SARs have taken over much of that performance space. Pipelines are still dominant in certain applications, like direct RF sampling. But this is not so much a fact of pipelines performing particularly well in that performance category, as it is a consequence of SAR ADCs performing rather poorly in that space. So what's the reason for this discrepancy? Why have some architectures done better than others? The simple answer is amplifiers. Conventional op-amps have not downscaled well into nanoscale CMOS, and this has led to a clear efficiency bottleneck. Conventionally, the more amplifier-intensive an architecture is, the less competitive it will be in nanoscale CMOS, both with regard to power efficiency and raw performance. But it also must be asked, should we even care about this amplifier bottleneck? If we're making progress with certain amplifier-free solutions, like SAR ADCs, why not just focus on developing those and retire linear amplifiers along with the architectures that depend on them? There are many in the field that argue exactly this, but I tend to think that it's a short-sighted philosophy. Diversity is always a good thing. The more tools we have in our circuit designer toolbox, the better. Not only does it provide more freedom for creativity in existing applications, it can also help to expand the boundaries of performance to new limits. A good example here is the emergence of pipelined SAR ADCs. At some point, people realized that by adding some amplification and residue gain into the SAR algorithm, you could expand the application space of SARs to significantly higher speeds. The key lesson in this is that however successful a technique is without amplifiers, it can potentially become even more powerful with the addition of them. Ultimately, we will be far better off if we can solve the amplifier scaling problem. Whether people realize it fully or not, it is one of the most profound constraints on design freedom we face today. Now, none of this is by any means a new realization, and to the contrary, over the last 2 decades, there has been considerable research activity focused on finding a general-purpose solution to high-efficiency amplification in nanoscale technologies, and more specifically in discrete-time switched capacitor circuits, which encompass not only ADCs, but many other baseband signal processing blocks as well. Any viable candidate must be able to operate in low supply voltages and provide linear amplification despite low intrinsic device gain and linearity. I'm showing a few of the most popular and successful candidates here, but this is just a subset of the ideas that have been proposed over the years. While most of them can improve certain aspects of performance or scalability, none are able to check off all of the items on this ideal amplifier wish list across all the metrics of speed, accuracy, cost, and efficiency. That's the real challenge, the holy grail of a general purpose solution. For example, a GMC or dynamic open loop amplifier does quite well in terms of speed and efficiency, but is severely limited in terms of output swing, gain, and linearity. For very specific applications like pipelined SARs, these limitations can be accommodated, but it does disqualify it as a candidate for a general purpose solution. And this brings us to the main topic of our talk today, the idea of a ring amplifier, or ring amp. It's yet another idea that attempts to tick off all of the items on the wish list, but the fascinating thing is, it succeeds at doing so. It's perhaps the closest we've come yet to a truly general-purpose scalable amplifier. This is what makes it an exciting topic to discuss. In this talk, I'm going to try to give you an idea of what a ring amplifier is, how it works, why it works so well, how to design one, and how to develop a ring amp topology that is best for your application. Let's begin with some ring amp fundamentals and cover the basic principles of operation. To begin with, consider what happens if we put a 3-inverter ring oscillator into a switched capacitor feedback structure. Notice that we've made a modification. In addition to the 3 inverter stages, there's also a reset switch and a capacitor. And during reset, this will store the input referred offset of this first stage inverter onto the capacitor, such that the trip point of the 3-inverter ring oscillator will be approximately VCMX, or 0.6 volts in this example. So after sampling some input signal onto the input capacitor and then configuring the MDAC into a feedback configuration, what we'll see in simulation is that the ring oscillator is going to drive its input node Vin, shown here in blue, towards its trip point. That's the basic principle of feedback operation. But because it's an oscillator, it's going to then continue oscillating around that trip point and never actually manage to settle into the final target value. But if we ignore for a moment the problem of being an oscillator and just think of it in terms of an amplifier and consider its properties in that sense, it actually looks quite attractive. We can generate large open loop gain by cascading multiple inverter stages. We can generate rail-to-rail output swing. We have extremely high slewing efficiency due to the large transient swings of biasing inside of the oscillator. We can make a small, simple, compact layout. It has inherent class AB biasing behavior and properties, so it's quite dynamic in its power consumption. And it's fully compatible with digital CMOS because we're just chaining together a bunch of inverters. So from that perspective, actually, it sounds great as a scalable amplifier solution. There's still just this one pesky problem, which is that it's an oscillator. But that's a problem that we can solve. We have to remember that there's a duality between oscillators and amplifiers. Any ring oscillator can be stabilized. It's really just a matter of putting the poles in the system in the right place such that we can generate a positive phase margin. To transform a ring oscillator into a so-called ring amplifier which is stable, we need to consider the poles in the system, P1, P2, and P3. Ultimately, to stabilize, we need to push one of these poles to a sufficiently low frequency relative to the other two, such that we can generate a positive phase margin. We have a few options for how to do this. One option is to try to stabilize by making an internal pole dominant. Another option is to try to make the external pole dominant. Now, in older technologies and more conventional op-amps, generally the approach for multi-stage amplifiers was to stabilize with dominant internal poles, using techniques such as Miller compensation. But this comes at a severe efficiency and speed penalty because that Miller capacitor injects a huge amount of extra loading into the system and slows it down. So why did people do that? Well, in older technologies, the device parasitics seen at the internal nodes were often in the same order of magnitude as the external load capacitance. So there wasn't really any other choice. As you can see in this Bode plot, to get a 60-degree phase margin, you need roughly 3 orders of magnitude separation between the dominant and subdominant poles. There's only one practical way to do that in older technologies, and that was to make a dominant internal pole. Now, as we've scaled deeper into nanoscale CMOS, that's not really the case anymore. The device parasitics of the internal nodes have decreased significantly due to scaling. However, the output load still has not scaled down because it's also constrained by KT/C and thermal noise requirements and other constraints that are independent of technology scaling. So with that external node still stuck with a relatively large loading due to KT/C, the strategy of stabilizing with the dominant output pole begins to make more and more sense in advanced CMOS. Achieving that 3 orders of magnitude separation in our Bode plot becomes a practical and attractive possibility. So ultimately, the benefit of going with the dominant output pole is twofold. It eliminates the speed and efficiency penalties of the excess loading presented by techniques like Miller compensation. And secondly, at the same time, it further decouples the internal pole frequencies from the non-scalable output load capacitance. Combined, this allows us to capture the maximum possible benefit from technology scaling, such that trends in ring amp performance improvements thus far show that it tracks very well with improvements in digital CMOS. Now, it turns out that we can do even better than that. In a very conventional, Class A type biased amplifier, the pole configuration and spacing of P3 to P1 and P2 is going to be statically defined, or at least as much as possible. In a ring amplifier, it's a much more dynamic system. And in the initial charging state, the poles will be spaced much tighter, such that probably, in fact, it will be even an unstable oscillator type of system with a negative phase margin, but a very high bandwidth, and so very fast operation. As a result of the dynamic behavior in the system, that external pole will be pushed down towards a lower frequency. And when properly designed in the steady state, it will land at a point where you have a positive phase margin and can have high precision steady state settling. But we have to be careful here, because actually the AC analysis that I'm talking about so far is really only giving us a small snapshot of the picture. Remember that an AC analysis is a linearization around a specific bias point. But in this system, we're dealing with large signal transient, DC bias type signals that are constantly changing. And so actually things like AC phase margin only tell us a small fraction of the total story. I think that a really nice example of this actually is found in this paper by Young Lim in 2015, where he shows a plot of a quote-unquote stable ring amp with 73 degrees phase margin, and yet in his system, it's obviously oscillating nonetheless. AC analysis is helpful in some ways for looking at steady state behavior, but actually in a ring amp, you have to really pay more attention to how do we actually get to steady state, and do we ever actually manage to lock into some stable bias point where this AC information has real meaning. So the full understanding of a ring amp, and also in the design and analysis of one, you absolutely do need to consider the DC and transient effects that are happening. And it's fundamentally a transient-based method of operation and sort of understanding and mindset that you need to bring to the problem. With that in mind, let's now take a deeper look at how dynamic large signal stabilization and feedback mechanisms in a ring amplifier allow us to go from any initial condition and transition from a potentially unstable configuration into a stable steady state configuration. The ring amplifier that I show here is kind of the classical ring amplifier that was first proposed. There's of course been many other structures that have been proposed in subsequent years, but I think this original one still works quite well as a teaching example, so we'll use that here for now. Fundamentally, the common characteristic that we see here and in all ring amplifiers in some shape or form is a splitting of the signal within the ring amp structure such that the output transistors of the ring amp are going to see a different version of the signal propagating through the structure. To see how this signal splitting leads to dynamic large signal stabilization, let's run a simulation of that ring amp structure within that switch capacitor feedback network. Here we have Vin in blue and the output of the first stage of the ring amp in red, the input to the PMOS output transistor in dotted black, and the input to the NMOS output transistor in dashed black. Now, in this initial example or simulation here, we have a dead zone of 0 millivolts. So this VDZ here is programming an offset onto these capacitors, and that offset is going to be 0. So functionally, we still have a 3-inverter ring oscillator here because there's no difference in the signal propagation through these two paths, and both output transistors are going to see functionally exactly the same signals on their gates. But as the programmed offset becomes non-zero, the gates of the output transistors in the ring amp are going to see different signals, and this is going to affect the transient operation that we observe. And critically, with some sufficiently large voltage programmed onto those offsetting capacitors, the ring amp will actually be able to transition from an unstable configuration and then actually lock and stabilize into a stable and constant steady state. And as we increase the programmed offset that we store into those capacitors, the degree of stability increases as well. Here we are with an even larger programmed offset and even more stability. And finally, a biasing condition where the ring amp becomes so stable that it almost immediately locks into a steady state condition. We can break the ring amp's transient operation down into 3 phases. The first is the initial slewing phase. In this initial phase, there's going to be a fairly large input signal that still needs to be settled by the feedback. And through the gain of the ring amp, this will lead to very large rail-to-rail inverter swings and a maximum overdrive bias on one of these transistors, but not both. In other words, in this mode, the ring amp operates like a bidirectional switchable current source, where you have 2 comparators which represent the front gain stages of the ring amp, and 2 current sources which represent the PMOS and the NMOS transistor of the output stage. One of these will be selected and will drive with maximum overdrive current onto the load capacitance. Following slewing, we enter into a stabilization phase, where dynamic large signal feedback mechanisms force the ring amplifier into a stable configuration. Let's take a closer look at how this dynamic stabilization works for the given structure. Starting with a transient signal at the input, as it passes through the gain of the first stage inverter, and then is shifted by different offsets on these offsetting caps, when they pass through the gain of the second stage inverters, they're going to appear on the gates of the PMOS and NMOS outputs substantially different from each other. We can see this behavior also in the example simulation, where again, recall the blue line is the input of the ring amp in feedback, the red waveform is the output of the first stage, and then the dotted black line is the bias, the gate bias of the PMOS output transistor, and the dashed black line is the bias of the NMOS transistor. Now, notice how these peaks descend and converge and pinch off the gate biases or the overdrive of the output transistors in this waveform. This is the critical feedback mechanism that stabilizes the ring amp. It starts when on some given oscillation period for a given offsetting value on these capacitors and bias condition, the average overdrive voltage is less on this oscillation period than it was on the previous oscillation period. And that means that there will be a proportional reduction in output current flowing from that transistor onto the load capacitor. And that then means that there will be a smaller amplitude of oscillation at the output compared to the previous cycle. And when it feeds back to the input, it'll also mean a reduced oscillation amplitude at the input of the ring amp. Then this will continue to feed back each cycle. On the next cycle, it will be an even smaller overdrive, and even less current, and even less amplitude, and then so on and so forth. So the example that I've shown so far is a fairly old school example. It's a Class B style ring amp, which fully cuts off its output in the steady state. And it's also simulated in a fairly old technology, 0.18 micron CMOS. Let's take a look here at a more modern example, a Class AB style ring amp that doesn't fully cut off its output in the steady state, and then simulated in 16 nanometer FinFET CMOS. It's basically the same story, and the fundamental stabilization mechanism is the same, even though the architecture is different, as we can see. Now, the specific way that this architecture functions, we're going to get back to that later in the talk. But the main thing to notice here for the moment is that even though we have much smoother curves that we see on the internal nodes and a stabilization point that actually has a non-zero bias where these output transistors are not fully cut off, the same basic principle applies of this progressive reduction in the overdrive voltage of the output transistors, which dynamically forces the output pole of the ring amp towards a lower stabilizing frequency. Now, another thing to notice here is that in addition to the internal stabilization mechanisms of the structure affecting stability, also the output voltage that the ring amp needs to settle to is itself an important factor that determines how well it stabilizes or how rapidly it stabilizes. And this is because for different output voltages, there will be different VDS across the drain source of the output transistors, and thus different output currents that are being squirted onto the load capacitance for a given overdrive pinch-off or progressive pinch-off that creates stability inside the ring amp. More specifically, for larger output values or larger output swings, you're going to have faster stabilization, but on the other hand, for larger output values, you're going to spend more time slewing. On the other side, if you have a very small or mid-rail differential output, then you'll need more time for stabilization, such as in the previous slide, but also you spend less time slewing. So this sort of cancels out in the end, it turns out. Basically, the total time it takes to settle is usually about even between the zero differential output versus max differential output cases because of the trade-off between the slewing time and the stabilization time sort of nicely canceling each other out. The third and final phase of operation in the ring amp is convergence into a steady state condition, where the output pole of the ring amp has already been pushed to a stabilizing frequency and the internal bias nodes are all converging into some stable final state. In the steady state condition, the dominant output pole is formed, which stabilizes the structure, and this is made possible by the large signal feedback mechanism that progressively pinches off the overdrive voltage of the output stage transistors, such that they'll be either in full cutoff or weak inversion in the steady state. In this biasing condition, there's a number of advantages that we get out of the structure. First of all, this means that there will be a low quiescent current on the output stage. There's also going to be noise filtering that we'll get out of this, and I'll explain that a little bit more in a moment. This also means not only do you have a pinched off overdrive voltage, but also as a result of weak inversion, your VD-SAT requirement on these devices is going to be very small, which means that you can have a very wide output swing on your output without running into compression problems. This, as a result, also means that you can get high linearity out of this structure, even under wide swing, nearly rail-to-rail conditions. Weak inversion also means that you will be boosting the RO of those output devices. So this output stage will have boosted gain in the steady state, and this also can help to boost linearity. Let's talk a little bit more about the noise filtering benefit that we get from this. Let's assume that the output transistors are in weak inversion. This means that their GM is, relative to the initial state, quite low, and they are going to act as a filter at the output of the ring amp, such that whatever noise is generated at, for example, the first stage of the ring amp, which would be your dominant internal noise source, as that propagates to the output transistors, they're going to be filtered by that weak inversion low GM output filter. This also goes for the other side of the gate source bias coming from the supply. So you can get filtering of both internal noise and supply noise due to that pinch-off effect. And it turns out that actually with smart design, the noise in a ring amp can be at least as good as that of kind of an equivalent op-amp with an equivalent amount of gain. But at the same time, the ring amp will be much faster and it will be much more power efficient. So in total, for a given noise budget, you're going to definitely come out ahead with a ring amp. Now, following from this discussion of noise and the role that the filtering of the output stage plays in suppressing that noise as it propagates to the output, it's also important to understand that SNR as a function of noise and THD as a function of nonlinearity may have different bias optimums, or at least have different sensitivities to bias as you adjust the biasing of the ring amp and the dead zone size. What we see in this plot here is a sweep of Ringamp bias control voltage around some nominal bias point here. When we go towards the left side of this axis, we are in a more underdamped configuration, and so that's the hard roll-off here is just due to instability. And on the other side, we have roll-off due to overdamped, where the THD is dominating, and actually this is essentially an artifact of the way we're calculating it, that SNR also rolls off. But essentially that's THD that's dominating here on this side due to incomplete settling. So whereas the THD looks more or less constant, and flat and nice across this range of biasing here in the central region, we see a very systematic increase in SNR as we move our output pole location to a lower and lower frequency. And this is as expected because it's consistent with this idea that there's a low-pass filtering happening in the output stage as noise propagates to the output. So the key thing to note here is that you may have different bias optimums for your SNR and THD. This here, of course, is one test setup for a given settling time and whatever else. Now, if you had less settling time, then the THD will roll off sooner. And so you need to pick a SNR which is essentially at the most damped case as possible, but still before the THD starts rolling off. And generally that's going to tend to be where your bias optimum actually lies. Okay, so let's summarize this initial section where we've looked at the kind of fundamental principles with a return to a look at the ideal amplifier wish list that we're trying to check off in order to make the ultimate general purpose scalable amplifier. On the speed side of things, we are able to achieve high bandwidth settling in the Ringamp due to the fact that there's a dominant output pole and high frequency internal poles. And this gives us a much better speed advantage than if we, for example, in the conventional sense, had needed to stabilize with an internal pole. On the slewing side of things, we also have a speed advantage. In fact, the Ringamp, due to its rail-to-rail biasing of the output transistors during slewing, gives us the maximum theoretical possible slewing efficiency and speed that you can achieve. On the accuracy side of things, due to the pinch-off of the output transistors, we saw that the structure is capable of nearly rail-to-rail output swing without compression. And combined with the cascaded structure of gain stages, we can also obtain a high open-loop gain in the structure, giving us, in total, high linearity across a large output range without compression. So that's in terms of THD, but accuracy in terms of SNR then comes down to the question of noise. And as we saw, the pinch-off of the output transistors also gives us an advantage there, where due to the filtering effect that it generates, we can get at least as good of noise performance of an equivalent op-amp, but with much better efficiency and other performance aspects. In terms of cost, the area of the structure is very advantageous or very attractive because we have this very simple, inverter-based construction. In terms of design effort, I would not necessarily say that this is a lower effort than a conventional design. In fact, it's probably a higher simulation effort because of the transient mode of analysis and verification that needs to be done. But in terms of the difficulty to the designer, I think once you get past the initial learning curve, it's not really any harder than designing an op-amp or more confusing. It's just a different mindset that you need to transition into. On the side of efficiency, the Ringamp, as I'll show later, can easily be designed for fully dynamic switchable operation. In other words, you can turn it on and off very rapidly in order to save power when it doesn't need to be used. And it has this inherent Class AB style operation. And then finally, at the intersection between efficiency and speed is the benefit of performance that scales like digital CMOS. And we certainly are able to check this off. not only on the speed side of things due to the fact that the internal poles are pushed at a very high frequency as a function of the technology node itself, but also because of the inverter construction of the ring amp, we have no limitation on functionality with supply voltage scaling as you go into smaller and smaller supply voltages in nanoscale CMOS. So far in this talk, we've looked at some of the more general principles of the ring amp in terms of its operation and benefits, but we've done so through a very specific filter of specific topologies and examples that I've shown you. In this section, I'd like to dive a little deeper into the different types of topologies that are possible in a ring amp and all of the kind of deeper and more advanced design considerations that are necessary for picking out a good ring amp topology for a given application. This decision tree shows some of the key considerations that you should keep in mind when choosing a ring amp topology. Dead zone embedding questions, the signaling mode to use, the number of stages to cascade in the ring amp, the common mode feedback to use, power cycling schemes that you should employ, and other considerations like auto-zeroing and high voltage structures. Let's go ahead and begin with perhaps the biggest and most important consideration, dead zone embedding. To begin with, we have to decide what sort of biasing mode we want to operate our ring amp in. Do we want to do class B, class AB, or class B plus AB, so some sort of hybrid mode? For a class B style ring amp biasing approach, you have in the middle of your input range a small input for dead zone, where actually the output conduction is 0 within this range, and both transistors are in cutoff. Now, surrounding this dead zone region are two weak zone regions, where even though there's some conduction of these transistors, they're in a weak inversion or pinch-off state, it's still a low enough output pole frequency that you can stabilize. And the benefit of this class B style biasing is that it's going to be the fastest and the most stable option. You can have a very high initial slew rate and high initial instability in your system. And yet, because of the presence of this dead zone in the large signal sense, it's still possible to charge into this zone and cut off inside of it and have rapid large signal dynamic transient effects for stabilizing. The downside, though, is that you will have excess distortion due to the presence of that dead zone because you're not going to settle any further once you're stuck inside of it. So I find that for a very fast course charging device, then Class B style biasing works very well, especially up to about 50 dB THD. If you want to go for higher accuracies, though, probably you're better with a different mode of biasing. Now, if you want to go for higher levels of accuracy, then Class AB starts to look more and more attractive as a biasing mode. In Class AB, across the input range, there's never any case where there's no conduction on the output. It's only weak zone. We've collapsed the dead zone, and the two weak zones on the edges are now joined together in the middle. And in that weak zone condition, we can now get the highest accuracy because there's no dead zone induced distortion. The only real error in the system in terms of distortion is going to be in feedback, the fact that we now have something that is constantly conducting like a kind of a regular op amp. So it'll have a classical steady state open loop gain. And of course, that open loop gain will have limited success in suppressing nonlinearities in the system and finite gain error in the summing node of the input and all of the classical issues we face. But that aside, you can get the highest accuracy with this mode of biasing. But the drawback, of course, is that all things else even, it will be a bit slower because you have a much narrower stability region in which to stabilize into. Now, it's also possible to go for a sort of hybrid approach where you have Class B coarse charging devices in parallel with a Class AB fine precision settling ring amp. This has been done also in regular op amps, the idea to have a coarse charge in parallel with a fine charge. But with a ring amp, it actually works out even more elegantly. And this is because those Class B biased coarse charge devices are going to have a dead zone, which when they get into their dead zone, they're going to automatically cut themselves off from the output and then leave just the Class AB device to settle in the steady state. So there's a very elegant handoff, like an inherent and natural handoff from the coarse charge devices to the fine charge device when you try to do this parallel approach with a ring amp based system. Now, once you've decided on the biasing mode that you need to use based on your accuracy and speed requirements, then the next question is, how are you actually going to do the dead zone embedding that will give you the dynamic large signal stabilization? First consideration here is the location of the embedding. You can either put it directly before the output stage or somewhere in the earlier stages of the ring amp. If we embed directly before the output stage of the ring amp, in this case using capacitors and in this case using a resistor, this gives us the most precise control of the output stage biasing. And for that reason, it's a very good choice for Class AB operation. Because, for example, in this resistor case, in the steady state, the voltage that forms across this resistor's terminals is going to also directly determine what the bias is on the output stage transistors and thus the output pole location as well. It's also good for high accuracy and linearity for other reasons, because if you have Class AB operation, then the accuracy of the feedback is only going to be a function of the open loop gain of the ring amp, and there's not going to be any distortion penalty involved. Also for low gain technologies, this tends to make the most sense, because actually Class B operation is rather difficult to make if you're low on gain, and the best thing if you're low on gain to do is to go for a structure that is Class AB biased. So in general, all of this sort of points towards this being a very good approach for nanoscale CMOS technologies, and is probably the most common approach used in recent designs that you see being published. But of course, this isn't the only option. We also have the choice of embedding in an earlier stage of the ring amp. And for various applications, this can make a lot of sense as well. In particular, this has the advantage of decoupling the stability and stabilization behavior of the ring amp from the large signal biasing at the output stages or the gates of the output stages. And this makes it in particularly a very good choice for Class B style operation when you're going for more high speed coarse charging performance at the cost of accuracy. Now, in addition to choosing the biasing mode and the location of the dead zone embedding, we also need to decide what sort of device we want to use. As you saw in these previous slides, you have choice of, for example, a capacitor, a resistor, or even a CMOS resistor. A capacitor embedding of the dead zone, whether in an earlier stage of the ring amp or directly before the output stage, allows us direct voltage mode control, where we can program a voltage across these offsetting capacitors, and this is what allows us to set or tune our stability condition. This in particular is best for Class B style biasing, for example in this structure here, and also for high voltage applications, and I'll discuss later in more detail why that's the case. The limitation of this is that, for example, if you go with this output stage embedding scheme, it's going to reduce the max possible slewing efficiency that you can achieve, because the offset voltage that you drop on this capacitor will come out of the maximum overdrive voltage that you can force onto these output transistors when slewing. So there is a slewing efficiency trade-off. By contrast, if you're looking to do the embedding directly before the output stage of the ring amp, and you do it with a resistor, you don't have this problem of dropping a series voltage in line with the gate of the output transistor. And so there's no penalty in terms of slewing efficiency when you do this. You can still swing rail-to-rail biasing on the output transistors. In fact, the mode of operation for this type of topology is a dynamic generation of that dead zone voltage. When it's initially slewing, the the first and second stage outputs will be forced all the way to one rail or the other, and select either the PMOS or the NMOS output with maximum rail-to-rail biasing. And there's no current in that moment of operation in the second stage inverter. And so there's actually no voltage drop across this resistor because there's no current. It's only in the steady state when you move towards the trip point and current starts flowing through the channels of the first and second stage that there will be a dynamic expansion of voltage over this resistor, which will then force the bias voltage of the output into its final steady state condition. Embedding with a fixed resistor can also have some advantages with regard to PVT robust design. Consider if either VDD increases or temperature decreases. This will lead to an increase in ID, or the branch current, and this will then expand the voltage across the resistor. And that is going to counteract the fluctuations in the bias and output current of the output transistors, helping to keep I out stable. On the other hand, there are some limitations to this embedding scheme as well. In particular, it tends to work best with a small embedding voltage because this also allows us to use a small resistance here. So if you have, for example, a large voltage that you need to drop across this resistor, for a given ID, bias in your branch current, if you want to generate a large dead zone voltage, then you're also going to need a large resistor size. Now the problem here is that that large resistor size is going to become relevant in the poles at the output of the second stage here at some point. So we have some parasitic capacitances on these nodes, and as soon as this dead zone resistor becomes a significant fraction of the R in our RC time constant, then that's going to start dragging down our poles at the output of that stage and reducing our speed capabilities. Now, it's also possible to implement the resistor type embedding device with a CMOS-based resistor instead. Benefits of this is, first of all, that it's tunable. You can, by setting voltages on the gates of these transistors, you can tune the effective resistance of the device, and also it's switchable, so you can switch between an on state where you have some resistance generated and an off state where it's cut entirely and it's high impedance in effect. So this makes it attractive for power cycling and switchable operation of the ring amp. And also for optimal biasing, or adjusting or tuning the bias post-fabrication. A limitation is that it turns out that this is a bit less PVT robust than the static resistor. It turns out that variation across PVT of this with regard to, for example, temperature or supply voltage is going to produce somewhat more variability than a static resistor, and so you'll need to design in some extra margin or have some sort of background calibration which can adjust the control voltage. There's actually quite a lot of options for embedding schemes and devices in a ring amp. Another idea that's been proposed is to use current-starved inverters. This is nice because, again, you can easily control the stabilization behavior and even dynamically control it during operation because you have a gate bias. So it works nice with analog PVT tracking schemes because we can create replica biases for this. But a limitation, for example, of this one is that it's going to tend to be slower because you're actually restricting the current flow in these paths here, and so your the poles of the output of the second stages are going to be constrained as a result. So maybe it's a little bit less optimum from an efficiency and speed standpoint. Another option is actually just to do the embedding in the devices themselves. So in the simplest ring amp, you just have 3 inverters chained together. And if you have a low enough supply voltage, which in nanoscale CMOS you very well might, that might just be sufficient enough already to create the dynamic stabilization effect that you need. And even if it's not enough, you can play with the the threshold voltage dopings of the output transistors as necessary. So for example, you could make the front stages ultra-low VT for speed purposes and then maybe standard VT on the output in order to get some sort of weak zone or dead zone region in the steady state bias point. So this can work very well if you have a low enough supply voltage in nanoscale CMOS, for example, and you can probably max out the speed area and simplicity with this approach because it can really be as simple as just 3 inverters. So that's rather interesting, actually. Limitations, for sure, PVT variation. Of course, now you're depending on doping of devices, so that's getting maybe a little bit complicated there. And of course, if you have a high supply voltage, then this doesn't work at all because you're just not going to be able to drop the offset needed in order to push these output devices into weak inversion or cutoff. Now, the next key consideration that you want to make when selecting your topology is going to be the signaling mode that you want to use. So far, we've just been looking at structures that are single-ended. And in some cases, that's actually what you're going to want to be using as a single-ended structure. For example, in common mode feedback paths, there's no differential signal. But for the main signal path in, for example, in ADC, you're almost always going to have some sort of differential signaling. So then you can choose between either pseudo-differential signaling or fully differential. If we go with the pseudo-differential option, we can just take 2 single-ended structures and tie them together with a common mode feedback. And the advantage of this is that you don't need to do any sort of fully differential configuration where you have a current source or a source-coupled pair on, for example, the input stage. And so this means that you can maintain the truly inverter-based, fully dynamic style of operation, and this can lead to the best speed performance if you go with the pseudo-differential approach because there's no current limiting in any of the stages of the ring amp. The limitations here is that, first of all, you have large input offsets that need to be canceled because the trip point of the ring amp is going to be a function of the threshold and random offset of the inverters in the system. And so you're going to need some sort of offset cancellation and storage onto, for example, here a reset switch and a capacitor in order to deal with the fact that the trip point will be a function of the threshold voltages of the first stage. So that adds some extra complexity. And of course, also with pseudo-differential, you're going to have maybe some limitations on accuracy or at least an upper bound on accuracy just due to the limitations of pseudo-differential in general. Now, going with a fully differential topology doesn't necessarily mean that much modification from the pseudo-differential. The later stages of the ring amp can still be the same as they were in the pseudo-differential case. It can be as simple as just tying the first stage together with some source coupling and some current limiting. So that can come with a moderate power and speed penalty, and of course you need to be considerate of the headroom overhead that you've injected by adding these extra devices in the current branches. But you're going to get in trade-off a more general purpose and versatile structure that's going to be able to achieve the highest accuracy possible. Another decision that we have to make in the topology selection is the number of stages that we want to use. The default number of stages in a ring amp is 3 stages. And this still remains basically the workhorse or the your average most general purpose case for most applications. With that in mind, there are some limitations that may make you want to consider other stages. First of all, 3 stages may not give you enough gain in certain technologies to support calibration-free operation if you're going for very high precision where you need a large open loop gain. And second of all, common mode feedback can be a little bit tricky in fully differential 3-stage topologies, where you may need multiple feedback loops in order to make sure that it's stable and doesn't have some sort of latch-up condition. Now, if you're targeting an application that needs high precision and you want to do it calibration-free, then you may need to have more gain in your system than what a 3-stage ring amp can provide. And then you can go up to, for example, a 4-stage ring amp that was demonstrated, for example, in this work here. Now, 4 stages is possible, but in order to have that extra internal pole, you may have more challenges in terms of, first of all, common mode feedback. You have to be very careful that you don't have latch up in the system. And also, you may have some challenges or sacrifice in speed versus power efficiency trade-off because of the addition of that extra pole in your system. On the other side of things, we also have the option to step down to just 2 stages. There's some special purpose cases where this can also be useful. In particular, in any case where you want a non-inverting feedback loop in a single-ended structure. For example, in common mode feedback, we have here in this MDAC a main signal path with a 3-stage ring amp, and then a non-inverting feedback path for the common mode feedback that we need that requires a single-ended ring amp. So we basically don't have a choice. We need to have a 2-stage ring amp structure in that case, and in the case of this common mode feedback, we don't need a lot of extra gain, so that works just fine. So for low precision applications, this can find a place, but the limitation is that, of course, you're going to have less gain because you have fewer stages. So if we can go down to 2 stages, why not go down to 1 stage? This is basically what has been called in other works something like an inverter-based amplifier or a class AB biased inverter amplifier. It's found in certain specialty applications and has been proposed as a scalable amplifier technique, but it has a lot of limitations. I mean, first of all, the gain is going to be very low, especially in nanoscale CMOS. And it also has very low gain bandwidth, so this is not a fast structure. It has a very slow settling characteristic. It has low slew rate and slewing efficiency because it has no gain in order to boost the biasing on the gates of the output stage. And so ultimately, a multi-stage ring amp is generally going to be both faster and more efficient than a 1-stage topology, even though it sort of deceptively looks like the single stage would be faster due to fewer poles in the system. It turns out that it's not actually. Common mode feedback is another important topology consideration. The best approach to common mode feedback in a ring amp is going to depend quite heavily on both the topology in terms of, for example, pseudo-differential or fully differential, as well as the general common mode requirements that you have in your system, like the level of common mode rejection that's needed or the common mode accuracy. A passive common mode feedback using just some capacitors and switches has the attractive benefit of being quite simple and rather easy to ensure stability for. And if the system specifications for common mode accuracy are not particularly high, this is often good enough. If the common mode accuracy requirement in your system is higher than what a passive common mode feedback can provide, it's possible to add some gain into the loop, for example, a 2-stage ring amp, in order to increase the common mode accuracy. It can also lead to a larger common mode input rejection range because of the gain's ability to steer more charge in the loop. In the case of a fully differential topology, both a global and local common mode feedback loop is often required. For example, in this 3-stage fully differential ring amp structure, the first path of common mode feedback is a DC bias path, where a DC bias charge is passed into the current sources of the first stage in order to set the current bias condition of that stage. The second path is a fast global feedback path tied from the outputs of the ring amp into this bias node of the current sources of the first stage through these coupling capacitors, and this provides an AC common mode feedback path. Finally, a third localized feedback path wrapped around the first stage of the ring amp helps to ensure common mode stability in the system. In order to maximize the efficiency of a ring amp, it's often possible to incorporate some element of power cycling into the system such that the ring amp only operates and consumes power when it's needed and otherwise is powered off. The best solution to this tends to be very architecture dependent, so you have to think for yourself a little bit. But we'll go ahead and look at some examples starting with this basic resistor bias structure here. Now, the naive approach to power gating a structure like this would be to put some power gating switches at the source side of the inverters, either on VSS or VDD side. But unfortunately, there's some complications that come with this and some drawbacks. First of all, there's an extra switch that you need to place in the feedback path because you're not guaranteed to have this PMOS device in this example to actually cut off. So if you want to make sure it's not affecting the output, you need this extra switch, but now there's an extra nonlinear resistance in the feedback path which could affect or degrade the settling performance of the amplifier. Furthermore, it has an undefined internal reset state which may be signal dependent, which means that there could be signal dependent charge kickback onto the input that could degrade the linearity of your system. Finally, there's this problem of headroom due to the power gating switches. And in order to make sure that the headroom penalty of these switches here is minimized, we're going to want to make them large switches, which means that then we need a large clock buffer in order to drive them, and we'll have quite a bit of CV squared F power associated with that as well. With some modifications, we can eliminate some of these drawbacks. In particular, we can add some pull-up transistors into the ring amp. And in the off state, this will then force all of the nodes in the system into a defined signal-independent configuration. So we eliminate the problem of signal-dependent charge kickback or coupling onto the input, and also we can fully disconnect the output. However, the addition of those pull-ups is going to add some extra parasitics onto those internal nodes, and in particular this node here and this node here, those are critical parasitic sensitive nodes where we want to have a very high internal pull frequency. Now, while that last topology was definitely an improvement over the first naive implementation, we can actually get even better with a self-resetting topology as shown here. This particular topology has CMOS resistors both in stage 1 and stage 2. And in the power down state, they will be in a high impedance configuration. And it just so happens to turn out that this particular topology puts all of its internal nodes not only into a signal independent state, but into a state that automatically cuts off the output. So the beauty of this is that there's no power gating switches required, and there's no pull-up or pull-down switches required. And on top of that, what is functionally our power gating switches in this case, these CMOS resistors, those are actually, in the on state, things that we want to have a significant resistance on. So we don't need to have large devices there. We can have small switches and minimize our clock loading to negligible levels. In applications that require a small offset, we also need to consider the possibility of using auto-zeroing techniques. Auto-zeroing usually doesn't come for free. It's usually going to require extra phases of operation, which means extra complexity of the overall structure and extra power consumption. However, some applications or topologies may require it. For example, it's common to want to do some partial cancellation in a pseudo-differential topology where there's a large inverter trip point offset present dependent on threshold voltage mismatch between the P and NMOS. When we do this sort of partial stage 1 cancellation and store the trip point of the first inverter onto an input capacitor, we also get the stage 1 random offset canceled for free as well. And then we just say that the mismatch and offset due to the later stages, since it's input referred and divided by the gain of the first stage, is small enough that we don't really have to care about it. In the case where you want really full cancellation and zero offset, then the input offset storage capacitor shown here needs to be programmed with the full offset of the ring amp in unity feedback. But we need to be careful here because the beta and load capacitance seen in this configuration is not going to be the same as when we put it into the primary feedback path. So we need to be careful when we design this with regard to the size of the auto-zero capacitance here to make sure that we can ensure stability and also minimize the noise impact. With the offset of the ring amp stored onto the auto-zero capacitor, we can then cancel its effect when we place it into the feedback loop. In differential topologies, you don't have this problem of inverter trip point offsets because your input pair is source coupled. So you really only have to worry about random mismatch offsets in the system. And in many applications, you can tolerate these offsets just inherently by design. However, in other applications, you may still need to do auto-zero. It's also worth noting that in many cases, there can be system-level methods that allow us to cancel the offset of the ring amplifier to acceptable levels without actually explicitly auto-zeroing it. For example, in this case here, we have a pipeline SAR stage that has some sort of input-referred offset of the ring amp. And by programming the opposite offset into the comparator in the SAR ADC loop, we can effectively cancel those offsets out of each other in the final output residue. For the most part, so far, we've been considering structures for low voltage nanoscale CMOS operation. But in some applications, you may actually want to use a ring amplifier for high voltage. And this turns out to also be perfectly possible, but some special considerations in different topologies are required. In this paper from JSSC 2019, we have an example of a high voltage ring amp topology. Here's their stage 1, stage 2, and stage 3 of their ring amp. And the first two stages are on 1.8 volt supplies, and the output is on a 3.3 volt supply. Now, capacitor embedding tends to be the best approach for high voltage ring amp topologies for a number of reasons. First of all, it makes it very convenient to drop the large voltage between the output of the second stage and the optimum bias that you want on your final stage transistors. Now, we discussed before why using resistor-based biasing to drop large voltages doesn't work very well, because that resistor then can lower the pull frequencies at these nodes. So the capacitor embedding is much more advantageous the higher voltage you go. The second key advantage is that it allows you to seamlessly shift between voltage domains. And so you can see they're up converting from 1.8 to 3.3, and with capacitors, it's no problem to make that conversion. And the final advantage is that with capacitors, you can couple into multiple different output drive strengths and transistor types and provide different biases to all of them. They're not doing that here, they're just using one capacitor, but if you want to, it's quite easy to have multiple output drive strengths, all operating off of a single stage 2. This concludes our discussion today about the considerations necessary for topology selection. Now let's move on to the question of, having chosen a topology to use, how can you optimize it for a given set of specifications? So let's assume that you've now chosen a ring amp topology that's well suited for the application you have in mind. After doing a mock-up and simulating, there's some performance targets that you're still not meeting your specs on. We can probably break these into two subcategories. You have your accuracy performance specs that you may want to optimize for example, THD in terms of settled linearity, and SNR in terms of noise. And you can have speed as a priority for optimization, which is sort of an orthogonal question. So let's start by considering how to improve settled linearity. The first option we have is just to reevaluate the biasing mode that we've chosen. For example, if we have more towards a Class B style biasing that has distortion in its characteristic, then we could adjust our structure, even our topology, to be Class AB biased instead. There's also the possibility of using circuit techniques to improve linearity in a ring amp structure. One that's been proposed recently is that of dead zone degeneration. So the idea behind dead zone degeneration for enhancing linearity is motivated by the observation that first order linear gain error in many systems is often easy to calibrate with either digital or trimming. But higher order nonlinear components of gain error can be much harder to correct. So for example, if you only have a 40 dB open loop gain ring amp, it may be 60 or even 70 dB linear if you ignore the first order component and just look at the effect of the higher order nonlinearities. And the idea behind dead zone degeneration is, well, let's try to make the gain error as first order as possible, and do this by warping the transfer function with regard to the output voltage of the effective open loop gain. And you can see that here on the right. We can see some open loop gain curves versus output voltage. And for different transistor sizes of this dead zone degeneration feedback circuit here, we can see that there's different warpings on the edges. And so how does that work? This feedback here is going to, for certain output voltages, turn on these transistors, and they're going to tap out some of the current coming from the stage 2 branch current, and they're going to tap that off and suck it into VCM or sync it. And if this is sized properly, we can see that actually this feedback action can flatten out your curve considerably and actually boost linearity by tens of dBs. Now, another pathway towards more settled linearity through the use of circuit techniques is to look at external gain enhancement techniques at the switched capacitor circuit level. This is usually compatible with Ringamp topologies because ultimately we're still working with feedback-based amplifiers. More specifically, class AB style ring amps tend to be compatible with this type of gain enhancement approach because the class AB biasing provides a well-defined open loop gain in feedback in the steady state condition, just like a regular op amp. A very popular technique thus far used with ring amps is correlated level shifting. The basic idea of CLS is to sample the output onto a capacitor and in some way then cancel the error on that output in a subsequent next cycle or set of cycles. In the conventional case, that's done by taking this capacitor, placing it in series into the feedback loop, and by inserting it in that feedback loop, it removes the signal from the output of the amplifier, allowing the input-referred finite gain error to be significantly reduced. There's a number of variants of this basic idea, and you find ring amps being used in the split averaging and weighted averaging versions of CLS in these works. In the circuit techniques we just looked at, first we looked at dead zone degeneration and saw how you could use that technique to suppress higher order nonlinearities such that you just have a simple first order finite gain error component that you can correct with simple digital calibration. And then we also looked at how you could use gain enhancement techniques, at the circuit level in order to provide some sort of gain boosting in order to deal with things like finite gain and compression distortion. Now, the other option is to look inward into the ring amp itself and consider ways to boost the gain of the amplifier. And there's two main ways that you can go about this. One is to cascade more stages. And we saw in the topology selection section before how you can have a 4-stage ring amp, and you could even go to even higher numbers of stages if you really wanted to, in order to get more and more gain out of your ring amp. The other option is to try to work with the stages that you already have and boost the per stage gain. Some people have proposed, for example, doing cascading of stages, some of the stages in the ring amp, in order to boost the gain of those stages at least. Other people have played with dopings of the transistors in various stages in order to get gain boosts out of those stages. I think in the end, the techniques that you use, whether at the circuit level or inside the ring amp level, and cascading or boosting, this all comes down to how much more settled linearity do you need, or how much more gain do you think that you actually need, and then you can kind of play with the technique that works the best without costing more than you absolutely need to spend. Now, if you need more speed, the first thing that you should look at and ask yourself is, have you done the best you can to minimize internal parasitics? And this really goes back to the fundamentals of what we talked about at the beginning of this talk, of trying to push the internal poles to as high of a frequency as possible. In fact, that idea, I would go so far as to declare the 2 commandments of high-speed ring amp design. First of all, you should never load the internal nodes unless you absolutely have to or have a very good reason for why you're adding capacitance to those nodes. And you should never limit the internal currents or GMs of the devices in the internal stages of the ring amp for the same reason. But in the designs that you see in the literature so far, a lot of people choose to break these rules. Now, sometimes I think it's actually just a mistake or misconception of the designer. But many times also there's a very good reason, and it comes down to that person not necessarily wanting to optimize specifically for max speed. They want something else. For example, I think this is a good example from 2015 where the author puts a current limiting clamp on the current of the first stage inverter. From a speed perspective, this definitely violates our second commandment there. But from an efficiency standpoint, you can get better current efficiency out of the structure by doing this. So there's of course other reasons and motivations for breaking these commandments if you don't care about speed. But if you do care about speed, you really shouldn't violate them. So if you've looked at your topology and decided that you meet those 2 commandments, then you can start considering circuit techniques for pushing your speed even further. And one of the most promising things that's come out in recent years is that of bias enhancement. So this idea of bias enhancement, which interestingly enough was independently proposed in these 2 different works, is to introduce additional splitting of signals inside the ring amp. So we have, for example, here the dead zone bias resistor that's already in place that gives us our stabilization behavior. But in the first stage, we have this option of adding this resistor here and then having kind of these cross-coupled connections, which are then going to boost the overdrive voltage of the second stage in the ring amp. So this gives us a speed advantage in that stage. And we can spend that advantage either by speeding up the second stage or by reducing the size of those devices a bit and reduce the loading of the first stage. And ultimately, you kind of probably want to balance both of those 2 things to get an advantage and push both the stage 1 and stage 2 output poles up to higher frequencies. And if we look at this in, for example, the results reported in this work here, we can see that actually, yeah, you can boost your bandwidth by a considerable percentage by doing this trick. Finally, if you've done everything clever that you can manage for boosting speed, and it's still not enough, then you can try increasing the internal power. And if you just burn more power in the internal stages, then you can push their poles to a higher frequency, which then allows you to also put the external pole to higher frequency as well. As far as reducing noise goes, your first option is just to increase the internal power. If you burn more power in the ring amp, then you can reduce the noise generated in there and therefore the noise that appears at the output. Now, your other option, and in fact the one that you should make sure that you've considered first, is to change the final steady state GM on your output stage. As we discussed before, as you go to lower and lower steady state output pole frequencies, you'll have more and more low pass filtering of the internal noise of the ring amp as it propagates and appears at the output. And so you first want to make sure that you have actually set your output filter location to an optimum bias point such that you're getting the optimum possible noise filtering and still meeting your THD and settling requirements. If you already are at that optimum point and you have as much filtering as you can get for this biasing without trading off THD, then you're going to have to probably pay a speed price in order to go to even more filtering. As you drop that pole to even further lower frequency, now you need more settling time in order to maintain your distortion requirements. Something that I find many people are interested in or sort of apprehensive about when it comes to ring amps is the question of PVT robustness and reliability. And I think a lot of this comes just from the naming ring amp and ring oscillator. It all sounds very unstable. So I'd like to take a little bit of time to talk about what can be done here and hopefully dispel some misconceptions. So the first thing to consider when discussing PVT for ring amps is the role that feedback plays in making our lives easier. If you compare it to, for example, an open loop amplifier like a GMC integrator that's very popular in pipeline SARs, for example, it's essentially the problem of balancing a ball on the hill. Any movement in any direction means degradation in performance. There's no feedback to suppress parameter variation, so you just need to make a GMC which can either be calibrated in the background to track, or something that is inherently PVT robust and has very little variation across corners. With a ring amp, you have a different situation. You have a feedback-based amplifier. So unlike balancing a ball on the hill, it's really more like we still have one edge of the hill there, but we've flattened with feedback the other side. And if we push the ball safely away from the edge of the cliff, then actually we're okay. So the feedback suppresses parameter variation. Of course, it's only as good as the feedback itself. So if you have insufficient loop gain, bandwidth, or stability to suppress those errors, then that, of course, will still result in some errors. But the main point is that feedback helps to suppress PVT variation. And I think compared to the open loop amplifiers that we see commonly used today, this actually is an advantage of a ring amp. So if you want to guarantee PVT robustness for your ring amp, you have two basic approaches. One is to just make it robust by design. So in other words, a calibration-free approach. Include extra safety margin in your ring amp design, give it extra bandwidth, extra stability, such that it can pass all corners, and maybe sacrifice some efficiency or speed in order to do so. So maybe you have to burn 20% more power to have 20% more margin. But this is kind of the normal trade-off that we make as designers anyway, even with conventional amplifiers to pass corners. You have a number of options for increasing that phase margin. You can either move the internal poles higher by burning more power, or you can move external poles lower and reduce your speed. And in fact, there's quite a number of designs that have come out with this calibration-free approach to ring amp ADCs so far, and I think they've made a quite powerful statement about what you can do. Not only have these papers demonstrated robustness across supply variation and temperature variation, in addition to also process variation, but they do it with really incredible figures of merit. So these are actually 3 ring amp-based pipeline SAR designs, and they all have totally state-of-the-art figure of merit. So it shows that even if you design with some margin and you make this thing PVT robust, you can still get very, very good efficiencies and state-of-the-art figure of merit. So the other option that we have is to use calibration. Rather than putting the ball safely away from the cliff, we can put it a little bit closer and use active bias control to hold it there. In addition to the obvious benefit of needing less margin in our design and getting better performance trade-offs, this also means that there's a lot more analog design freedom opened up, because you can now consider topologies and circuit ideas in the ring amp design that maybe aren't so PVT robust, but with some sort of background tracking are still viable solutions. The trade-off, of course, is that you're going to have more digital complexity or maybe analog complexity if you go with an analog control for tracking. There's only been really one calibration-based Ringamp ADC reported yet, but I think that we're going to see more to come. And in the early data that we have, anyway, it shows that this approach also can achieve breakthroughs in the state-of-the-art. So I think that probably what we're going to see is that both approaches of both robust by design or robust by calibration are going to be something that people are going to be using in the future, much like we see with, for example, open-loop amplifiers, where both of those approaches have been developed to the point that they can be industrialized as well. As a final section in today's talk, I'd like to tie it all together with a practical design example. The first thing to consider about design and validation of a Ringamp-based system is that it's fundamentally a transient system, and so it means that there has to be a transient-centric design process. And this is in fact actually not unique to ring amps. In fact, all next-gen amplifiers, including ring amps, but also GMC, GMR, charge steering, zero crossing, etc., these are all fundamentally transient domain techniques. Luckily, modern compute power is up to the task, I think. What I find is that if you have a decently powerful server and multi-core APS licenses and cadence, then that's more than enough to handle the design and validation requirements. In terms of methods of analysis for day-to-day design of the ring amps, the first tool that you can use is just transient waveform visual inspection. And in particular, I like to look at the input nodes of the ring amp because these are the nodes in feedback that are trying to drive to the same value. And so you get a pretty clear picture of how your slewing and stabilization and settling phases are performing, and you can really get a lot of information out of those signals. Now, if you want some quantifiable results or numbers that actually tell you what your performance levels are actually at, then one of the best ways to extract that is by running a signal into your system through the ring amp and then sampling it at the output, whether as an analog residue or capturing it through digital quantization, and then running an FFT on that. You want to make sure that you, first of all, exercise the full output swing of the ring amp, so you need enough sampling periods that there's enough different output residues that you can see how it operates and how its stabilization behavior is for the full range of its possible output values. And also, you want to make sure that you have enough FFT points. So, for example, if you're just looking for a coarse bit of information about SNDR, well, maybe you can use fewer points, but if, for example, you want to know information about linearity and see what levels your harmonics are at, well, you're going to need to run more points in order to get your SQNR floor down low enough that the harmonics and nonlinearities will pop up and be measurable. When running these transient simulations, I would recommend going as quickly as possible towards doing your analysis in an in-situ test bench that's as realistic and accurate as possible to the system that you're actually going to be placing the ring amp in. So this includes not only real switches in the system, but using the actual feedback factor that you'll have, real loading conditions, timing control schemes, estimates on your parasitics, any other non-idealities. All of these things can have a pretty profound impact. In fact, there's even some papers that show that the switches in the system can add extra poles and zeros into your settling behavior, which in some cases you can even exploit, but in many cases can also be a problem for you. So the sooner you have an idea of how it operates in the full system, the better, and you don't really actually know the performance until you get to that point. So I'm going to show you some simulation results of an in-situ test bench with a ring amp structure, and the structure that I've chosen is this one here. And hopefully after the discussions of this talk, it'll be a little bit easier to piece together what we have. First of all, we can see that it's a fully differential structure with differential inputs into the first stage and then sort of a single-ended sort of construction for the second and third stage. You can see that it has a resistor-based dead zone embedding directly before the output stage, and that we're doing this with a switchable CMOS resistor. We can also see switchable CMOS resistors present in the first stage, implementing bias enhancement for better speed performance. And recall again that for this particular construction, you can switch off all of the CMOS resistors and you'll automatically have a very elegant self-resetting behavior without any extra power gating switches or pull-up switches. So this is a very low parasitic high-speed architecture. And finally, we can see that it has a multipath common mode feedback. So we can see a DC path coming in through here that charge biases these gates. We can see an AC path coming from the output to the common mode feedback through these capacitors. And then we can see a local feedback around the first stage through these transistors here. Okay, let's go ahead and put that ring amp into our in situ test bench, in this case a 1.5-bit flip around MDAC, and we're going to put some signals in. Now if we look at one of the samples that we capture, we can see, for example, the output residue being generated for a given period of operation. We can also see the X nodes, so the summing nodes, at the input of the ring amp. And what we can see here is, okay, as we come out of slewing, we have fairly rapid stabilization and nice settling. So this is what I would say a pretty good waveform. So in this test bench, as we're optimizing our design, the first key parameter that we can play around with is the output drive strength. If we go with a smaller drive strength, we scale down the sizing of the output stage. Then, of course, this will make us more stable. And also it gives us less internal loading, but it also means that our slew rate will be reduced. So there's a trade-off there, and we can see, okay, we now have a lot slower slewing, but we almost immediately go into settling. On the other side of things, if we go to 2x output drive strength, well, we slew a lot faster, but our stability is considerably worse for the same bias condition. But let's say that we really do want to go faster. We really do want that fast of a slew rate. Well, then we have another key parameter that we can adjust. We can increase the size of the internal stages. If we burn more power there, then we can push their poles up to an even higher frequency, and we can regain our stability. And so we can see here we have that extra double slew rate at the output, and yet we're still able to get stability due to the power that we're burning extra in the internal stages. Another key parameter that we can adjust is the dead zone biasing. If we go with a smaller dead zone, then we'll have faster settling, and a larger one will be more stable. So it's a pretty obvious knob. Here we have our nominal case again, where we have kind of an ideal operating point that we're happy with. And if we were to expand the size of the dead zone or otherwise add extra pinch off and reduce the overdrive voltage of the output stage transistors even further, well, we have really nice stability, but we can also see that we're kind of in a class B mode here. There's this gap where we've created an actual dead zone, and it's not settling into that dead zone. So we're generating distortion by doing this in trade-off for very good stabilization. On the other side, if we have a much smaller dead zone where we have a lot less pinch off, well, this means that our output pole will be at a higher frequency now. And so our phase margin is much worse, and our stability and settling is much worse. So on the other side of things, also, we have a problem of being underdamped. So to summarize, if we take all of these key tunable parameters, we can try to make an example design procedure. Starting with our in situ test bench, we can initialize a ring amp with kind of over-designed front stages. So let's just give extra bandwidth to the internal poles, and then go ahead and size our output stage for the slew rate that we want. And then once we have that set, we can downscale the front stages for power efficiency. So for example, I've found that a ratio of 4 to 2 to 1 can usually be a pretty nice one for a high-speed ring amp anyway. And then we can iterate through 3, 4, and 5 as necessary until we arrive at a design point that we're really happy with. But of course, this is just an example procedure. I mean, ultimately, I think it's going to depend on a lot of factors specific to your design and what you're optimizing for. So you're also just going to have to be a good analog designer and think cleverly for yourself on this. To conclude, I'd like to go back to the very beginning of the talk where we talked about diversity in circuits. And we had talked about this amplifier bottleneck reducing diversity. Well, with the breakthroughs that we're seeing with ring amplifiers, this is opening up a lot of interesting possibilities for new architectural freedoms, new applications, and generally just going after ideas that maybe are amplifier intensive in a way that previously was disqualifying. Now that's not such a big problem. And we're benefiting already from that, and you can see that in the papers coming out in recent years. So to provide a case study, for example, our paper at ICCC in 2019, this was a direct RF sampling ADC that we presented, which has, if you take SNDR, SFDR, and power efficiency all together, it really represents an order of magnitude improvement in the state of the art for that application space. And the notable thing about it is that we did it with 36 ring amps in that system. So it's a very amplifier intensive architecture compared to most approaches that people take these days. And yet we were able to break a lot of records with it. And so I think that represents well this overall point of the benefit of having more tools in your toolbox. Now, if we look at how ring amps are helping to shape the design ecosystem, we can see that at the moment it's still rather lopsided. In particular, it skews towards ADCs and specifically pipeline and pipeline SAR architectures. But I think what we're going to see over the next couple of years is a shift into new domains and new design spaces. Very recently this year, we're starting to see ring amps show up in LDOs, and people are realizing how to use those to their advantage. In Delta Sigma ADCs, we're starting to see some things coming out, and I think we'll see more of those in the future. And really, actually, the sky's the limit here. There's a lot of open space here for looking at how ring amps can solve problems in a lot of circuit domains that's open for the taking, I think, for people who are interested in considering that. As we see ring amps expanding into more and more diverse sets of applications, we can also expect to see more diversification of the core principles as they're implemented in actual physical structures as well. So based on that, core set of ideas of multi-stage amplification with dynamic, pole reallocation and output pole stabilization, based on that core idea, we already see, in the early years of ring amps, many different ideas and variations on that theme. And I'm showing here just a small subset of all of the things that have been published thus far. And then also things going into, interesting new directions and beyond. Like, for example, it's interesting to see hybridizations happening. For example, the closed loop dynamic amplifier that has been recently proposed is kind of a hybrid of a dynamic amplifier and a ring amplifier. So we kind of see these concepts or ideas, spreading out into very diverse implementations. But I still haven't answered the question that I posed in the title of this talk. Is the ring amp the scalable amplifier that we've all been waiting for? Well, actually, I should rephrase the question. The question is it the scalable amplifier that you've been waiting for? And I guess that depends. They're an exciting new tool, and it could be the right one for your task. There may be other solutions out there or other tools that are a better choice for what you're trying to do. That's the beauty of circuit diversity. So think about it, and I think decide for yourself. And with that, I conclude my talk, and I thank you very much for your time and attention.